Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this time we have just to meet together and study your creation. I just pray that you'd guide my thoughts today and just help us to accomplish something with clarity that your name I pray. Amen. So I wanted to try to just kind of start back, try to do a little bit more quantum mechanics with you guys, and I'm probably going to assign you a few heat equation or wave equations to solve, with specific initial conditions and so forth. I'll email you those. I have not had a chance to pick them out today, so. Alright, so basically we need to settle some notation to start with. So in quantum mechanics, tend to use the following notation for the state, like alpha or beta or gamma. These are so-called kets, all right? This is half of a horrible pun. And then you talk about the inner product. The inner product is something like this: beta, alpha, and it's defined to be such that it's equal to the complex conjugate of alpha beta. This is the property of the inner product. It's a complex inner product. So the alpha, the beta, the gamma, these are state vectors, all right? Let's see, what do we have? Some usual stuff, like alpha is greater than or equal to 0. If you have alpha equal to 0, that's true only if alpha is 0. So it's like, it's inner product. And you have linearity in the second slot, like C1 beta plus C2 gamma is equal to C1 alpha beta plus C2 alpha gamma. But in the other side, you end up with complex. You pull out complex conjugate scalars. All right, it's not bilinear. It's these could be complex scalars, by the way. Okay, C1 and C2 are complex numbers. All right, and then typically what you're looking at, these are elements in some vector space of physical states, and you oftentimes want orthonormality, something like this: the ith state and the jth state gives you Kronecker delta ij. These are orthonormal states. I'm not telling you guys anything terribly new here. Mostly I'm just trying to get you acquainted with this notation. So let's see here. If we have, let's see here, I need to move on. Let's see here, I can say this. If alpha, right, is, oops, sorry, wrong way. If alpha is equal to the sum of a sub I, alpha sub I, right? Then if you take alpha sub j on alpha, what happens? You get right? So by linearity, I can pull this out. I can pull the constants out, right? This is an orthonormal basis. Kronecker delta ij, and so what do you got? You got a sub j, right? So here you have that a sub I is equal to alpha I on alpha. In other words, you have this identity. You can rewrite the ket as sum over alpha I, alpha, alpha. Sorry. Oops. Oh. Minimum momentum. Too many alphas. Breaking my brain. So yeah. So this would be alpha I, alpha, alpha I.
It's 5 o'clock.
Worries me slightly because it's not quite what I remember. Alright, let me move on here.
So wait, that's like like operations. That's like alpha sub I dotted with alpha multiplied by a sub I ket.
Right, it's just like that expansion we found close to where we discussed Gram-Schmidt and linear.
Okay.
Right. So orthonormal basis expansions are nice.
Okay.
So we try to work with orthonormal bases. We also talk about eigenvalues and so forth. So if you have an operator T on this vector space of states, if we have T alpha equal to lambda alpha, that makes, of course, this, an eigenvector of T with eigenvalue lambda, right? Now, when we put a hat over things, they're operators in quantum mechanics. That's like the common notation. You put a hat on things, they're operators. Things without hats are scalars, generally. All right, so the way the inner product works, well, I should say that. If T is Hermitian, you have the following. The conjugate, the dagger, and conjugate transpose. Well, whatever that means. Let's see here. You have this equation. Let me just say that. Try to unwrap that more as we go on here. Let's see here if I can explain that further. See if I can unwrap that. So here's what I have. I've got alpha T hat beta, all right, is equal to, what's it equal to? What? All right, fine, just hang with me here. What I say is A transpose the matrix of, now I'm assuming it's like finite dimensional just for the sake of discussion, standard matrix of T, B, so this is like the column vector corresponding to this state beta. This is the row vector corresponding to state alpha. If the set of states is finite dimensional, we can represent them with row and column vectors in like Cn. That's what I'm thinking of here. And so let's see here. By sock shoes, this is the same as the conjugate transpose of the conjugate transpose of that. Conjugate transpose is the thing again. So that's A. Conjugate transpose B. Okay, so then that is the bra vector. T. It's the vector that comes from this abstract vector, T dagger acting on alpha. And there's the rest of the verbal pun. This is the bra. This is the cat. Together, they are a rocket. True. But horrible. Alright. I don't know. This is kind of circular, what I'm saying at the moment. Let me be a little bit more explicit here for just a second. It's helpful to stop and take a look back at CN and the inner product on CN. Right. So if we look at V equal to Cn, where you have the inner product V with like W equal to V dagger W, where that means that is actually V conjugate transpose times W, literally that, right? There's an identity. If you have a linear transformation, T of V, here, W.
Your camera setup may be failing.
Oh.
Sorry.
Well, I'll give you a chance to. Is it okay?
Is there like a way to tighten the center or something?
No, it's unstable, but.
Is there an eraser? Hold on. There we go.
Okay.
Awesome.
So, let's see here. So, I mean, in the case of an ordinary dot product, if you have like T of A dot B, I think there's an identity that basically says, excuse me, if you have, stupid, if you have AV dot W, right, then that would be AV transpose times W, right, which would be A transpose, V transpose A transpose W, right, which you could rewrite as V transpose times A transpose W, which you could understand is actually V dot A transpose times W. So all we're looking at is like the complex analog of this identity. This is true for any operator. Alright, so like, if I have this, then that is, it's the matrix of T, V conjugate transpose times W, which is V conjugate transpose, the matrix of T conjugate transpose times W, which then is, by the way, V conjugate transpose times the matrix of, so by definition, you could say the conjugate transpose of the matrix is the matrix of the conjugate transpose transformation. So like that. And then that's exactly V T conjugate transpose W. I know there's some linear algebra going on here, but my point is really that this is just an identity for any transformation. I mean, this does not give the matrix, the transformation, this is not a property of the transformation, this is an identity of the inner product. Okay, so why is this, now over here, the thing I was reading from, right, and so these notes are based on, I think, Griffith's, and maybe my notes from undergraduate quantum mechanics. So basically he says definition, alright, definition T is a Hermitian operator, right, if the inner product of T, right, T alpha beta is equal to what the no. Well, anyway, this is what the definition should be. My notes could be wrong, I wrote them 4 years ago, under who knows what circumstances. All right, so this is alpha T conjugate transpose beta, right? So if I just erase that and just put a T there, that defines a special kind of operator, a so-called Hermitian operator. So like a Hermitian operator basically has T conjugate transpose equals to T. This makes Hermitian. Okay, so suppose you have a eigenvector for a Hermitian operator, all right? So suppose you have T hat acting on some vector gives you back lambda acting on the vector again for T Hermitian. Then what can we do? I mean, I could prove other things, you guys. Like, if you have distinct eigenvalues, you get orthogonal vectors, right? And you could also argue that if you have a Hermitian operator, you can obtain an orthogonal basis of eigenvectors. It's a little bit more than that, though. That's a spectral theorem. The term spectral actually comes from our current discussion, where the spectrum is talking about like the energy spectrum, and the operator is the Hamiltonian. So the eigenvalues actually are energy, and that's why the spectral theorem is called the spectral theorem, because of the application to physics. A lot of the growth in early, functional analysis in the early 20th century is in no small way tied to the questions which arose in quantum mechanics in the same time period, 1920, 1950, somewhere in there.
I did always wonder why it had a special name like that.
Yeah. Has to do with checkered physical past. So here, right, okay, so what happens if I take, say, alpha, right, T hat? So suppose I act on, I act on this thing, right? Like this. Here's the question of what that means. So I'm taking the inner product of, let's say, look at it a different way. I'm taking the inner product of alpha with this vector, right? But that's equal to what?
Lambda bracket alpha.
Alpha, yeah, lambda alpha.
But the lambda passes through, right?
Right, which is lambda alpha alpha. We assume we're working with, well, let's suppose that we've normalized the state, right? We can normalize it to length 1. So work with an orthonormal eigenvector. A normal eigenvector, normalized, right? So that's just lambda. But, right, on the other hand, basically by the definition, like so, this is equal to T dagger, right? Because it's Hermitian. And so by the general identity of operators, this is T of alpha, alpha, right? And this is lambda alpha alpha. But when you pull scalars out of the other side of the complex inner product, remember it's not bilinear, it's sesquilinear, it's 1.5 times linear. So when you pull scalars out this way, they get complex conjugated. That's the that's the structure here mathematically. And of course that's lambda star. And so as you can see, the circle is complete, and we have proved that Hermitian operators have real eigenvalues.
Because the conjugates have to equal each other, therefore the complex.
Right. If the complex conjugate of a number is equal to the number again, that means it's a real number. The imaginary part is 0.
Can we show proofs like that on tests?
What, like the full Manga style square loop proofs? Yeah.
points for that.
If you say by the square manga style proof loop technique, maybe I don't know.
The Fruit Loop.
The Fruit Loop. No, proof loop. Proof loop.
It's forever now, the Fruit Loop technique.
No, it's not the Fruit Loop technique. Take it back. No, you definitely can't use it. All right, let's do it. Moving on.
But the Proofy Fruit Loop.
Moving on.
Sorry.
It's okay. All right, so this, generically speaking, is the kind of like linear algebra we have to do quantum mechanics, because there's some vector space of states. Those states represent a particle or system, and then we have operators that act on the states, and that tells us about the probability that that state. Well, anyway, let me go on here. So this is the sort of abstract Bra-Ket viewpoint, right? Which is related to the wave function stuff I was showing you guys before, right? Like, basically, these are just two different notations for the same beast. So, like the function, I mean, this is, if I write this, maybe you can see the connection. So the bracket of f and g is the integral of f star of x, g of x dx, right? So there is something new here, because I'm using not just the functions, I'm also using sort of the dual to the function. So if the functions are the vectors, we're also using the dual vectors to the functions. We're using like both in the discussion here. There's a natural pairing between vectors and dual vectors through the inner product. And so anyway, we consider functions, right, with what do we need for the functions? They need to be so-called square integral functions, right? So that's the integral, the modulus of the function squared, right? That has to be less than infinity, otherwise we can't normalize that state, right? All right, so now that we have all this, we can actually ask a specific question. We're starting to play in this mathematical wonderland of quantum mechanics. I don't think we've quite made it physical yet, but starting to show you the toys we play with. Here's a question. If we look at t hat equal to ddx, and we look at the set of states defined by just functions, all right, square integrable functions on the reals, right? The question I have is the differentiation operator Hermitian? All right, so let's calculate it. So we look at f, some function, I don't know which one, and then the differentiation operator acting on g. So that would be something like, and actually I'm going to be more specific. Say it's the integral from a to b. All right, we'll focus our attention here on some closed interval. Although I suppose we could take a going to minus infinity and b going to infinity, if you like. All right. And so this, by definition, is f star of x dg dx dx, right? And let's see here, guys. How do you move a derivative? Like, okay, so basically I want to move the derivative to f in order to investigate whether or not it's Hermitian, right? Because if it's Hermitian, we should be able to do what? That would mean that f d hat of g is equal to d hat f g. That's what basically Hermitian means. You can move the operator from the bra to the cat with no cost. That's tantamount to saying that if we're working on a finite dimensional vector space and you look at the matrix, the complex matrix, then the matrix is equal to its own conjugate transpose. So in the context that the vector space is finite dimensional, it breaks back down to what we meant by Hermitian matrix, but this also allows for like function spaces, which could be infinite dimensional, so it's not standard linear algebra. Now, so to do this, we do integration by parts. So this is the integral from a to b, ddx of f star times g minus df star dx times g dx. Just by product rule, right? And so then, by fundamental theorem of calculus, that's f star g, evaluated from a to b, minus the integral of df star dx g dx. So, looks like we've got this term minus the bracket of df and g. Now we can make that term go to 0 if we assume that our wave functions, our f and g, have the condition that they vanish at the boundary of the space. Or it could be that they have to vanish at infinity, or minus infinity. That's certainly going to be something that's part and parcel of, like, we're not going to get this as less than infinity if we don't have that vanishing condition anyway, so it's not so unreasonable to suppose that this part goes to 0 by the boundary conditions on the wave functions. Alright. But then again, we're stuck with this, minus df, so no, I'm not going to do it. So no, the differentiation operator is not Hermitian. Now, these operators are going to be manifestations at the quantum level of physical things we already know about. What physical things do we know about? Like the position of a particle, the momentum of a particle, things like that, right? These measurements, momentum or position, these are real numbers, right? So it turns out that I'm going to explain that the eigenvalues of the operators represent the actual, sort of classical measurements. And so for a operator to represent something that we measure classically in terms of a real number, it has to be a Hermitian operator, because those are the ones with real eigenvalues. So what this kind of shows me is that the differentiation operator, just the straight up differentiation operator, does not represent a real physical observable, because it's not Hermitian, so it doesn't have real eigenvalues. All right. See here. So, but the fix is in. It's not much to do. So what you do, here's the answer, so to speak. You let T1, I'm calling it T1, I don't know why, equal to, it's not, I guess it's just I d hat, right? Just multiply the differentiation operator by I, right? What happens?
For this specific case, we're still taking t hat to be the differential operator?
Yeah. Oh, yeah, sorry.
Okay. I don't have those different t.
No, I meant the same D, yeah. So if you can just kind of follow along up here, right? I, right? I, right? There's an I here, I suppose. There's an I here. I guess there's still an I here. Now here, in order to pull the I inside the derivative, right? I would have to, if I put the I here, right? And I put parentheses, that makes this a plus. And there you go. That's Hermitian. You can pass it from the broad to the ket without alteration. Okay, so if this is this I times the differentiation operator, what's its eigenvalue? What's its eigenfunctions, rather? What are its eigenstates? Sorry. Oh, man. So we're trying to solve, like, I d hat, right, times f is equal to like lambda times f for some lambda. and well, some f and some lambda, right? Now we know lambda's real because we just proved that ID is Hermitian. So this is really df dx, right? Equals to minus I lambda f. Oh, that's exponential growth. That's just like y prime equals to ky, but the k is complex. So we can easily see that the solution to this is something like f of x equals to e to the minus I kx. Lambda. Sorry. Does that work? If you differentiate that, you get back minus I lambda times e to the minus I lambda x. Yeah, so then we multiply both sides by I, we get I ddx. Acting on f equals lambda f. There we go. For which lambda? Do you have any suggestions about what lambda can be? I mean, lambda has to be real, since this is Hermitian.
You said this was exponential, right?
Yeah.
So it's...
There is no restriction, that's kind of my point. There's lots and lots of eigenfunctions. Just like,
narrow down to one, like,
you know, when we look in linear, when we were first talking about eigenvectors, I usually try to throw out the differentiation operator as an example.
Mhm.
And I mentioned that, like, e to the lambda x is the solution, and lambda is the eigenvalue for any lambda. I usually use a there, maybe. My next example here, by the way, a Hilbert space is a complete inner product space. What's that mean? It's like a vector space with a complex inner product. The completeness means that every Cauchy sequence converges. So basically it's the notion that space doesn't have holes in it. You guys talk more about that in real analysis. I think we talked about it some in advanced, but if you
Hilbert spaces or Cauchy?
the complete, what is a complete space?
Oh, complete space, sorry.
Like, I think I may have you guys prove that like the set of matrices was complete, perhaps. I think in class I proved that Rn was complete. Or maybe I had you prove C is complete. Anyway, it means it's got no holes. Alright, so how about, there's another one I look at here, which is kind of this one you're going to like, Jess. This one, that was 1. 2 T2 acting on F, I'm defining to be just X times F. So just multiply by X. This is a linear operator. And what's its eigenvector? So
X is what here?
like X. So if this is at X, this is equal to X times F of X.
Okay.
I mean, it's just,
I almost thought it was scalar.
yeah, multiplication by the x coordinate. Now, like for example, if your function was e to the x and you feed it to the T2 operator, you get back x e to the x. Okay? Now, here's the claim, is that the eigenvector, in this case it's really an eigenfunction, of course, but, well, it's not exactly a function. This is an eigenfunction. Alright, so let's see if we can, how would we, let's see how to how to do that. Show that's an eigen. I mean, so the claim is, he's claiming that, I guess I'm the he, T2 hat, when it hits delta of x minus lambda, you get back, what's the, so that's x, okay, so that's x times delta of x minus lambda, right? But if you think about that, right, how does that work? Now think case-wise. Check it out, think case-wise. If x is not equal to lambda, 0.
0.
If x is equal to lambda, it's non-zero.
So it's just going to be x.
So if you think about the cases, I can just as well write lambda delta of x minus lambda, right? Because the only place it's non-zero is when x is equal to lambda, so that's the same. Bam, eigenvector. Eigenvalue lambda. That's some formal nonsense right there. Now this should actually be understood, of course, in terms of integration. Fine. Let's see here.
Like understood in the terms of integration, as in like integration like with the Dirac function, like those two functions being multiplied. Is that really necessary?
Well, I mean, I just think that's sort of a generic comment. If you want to understand the direct delta function, any statement about direct delta functions to be understood carefully, probably you have to write an integral. That's just my feeling. But anyway, okay, so if I have an operator, right, and if I have a state, come on. I wanted to do something here before I... So like, let me just skip ahead just a bit, and then I'll go back. But oh, maybe I shouldn't. No, let me. You know, I actually thought about these notes for a while. I gave like 3 or 4 lectures at the end of Physics 2 one semester. I actually did this in Physics 2 at the end, when I had a particularly strong class. I only tried it once.
Didn't go well.
It was appreciated by 2 students. Alright, so let's see here. But it was worth it. I now have these notes. Let's see here. And now that I remembered them, they are serving the purpose again. Alright, so the point of these 2 examples is that T1 and T2 both have continuous spectra. In other words, their eigenvalues could be anything. Totally unbounded, right? But this is a great contrast to the discrete spectra of the infinite square well that we looked at the other day, right? Or the quantum harmonic oscillator, which I'll hopefully work out. Beyond this, something else I should point out, of course, is that e to the minus I lambda x and the Kronecker of x minus lambda, these are not square integrable functions. These are not square integrable functions in the Hilbert space, right? So what does that mean? I'll tell you what it means. Is it means the concept of Hilbert space is actually a little bit too limited for quantum mechanics. What quantum mechanics is actually done over is not quite a Hilbert space. It's something called a rigged Hilbert space, which is going to allow things like this. Don't ask me the technical details. My advisor spent the better part of weeks setting it up properly.
Did you say, what was the definition of Hilbert space again? Was what you defined before with it in terms of Cauchy, was that complete or Hilbert?
A Hilbert space is a complete inner product space. So like Cn, for example, just the complex n vectors
Okay.
with the usual inner product is a complete Hilbert space.
Okay.
Lots of things are. Just this, this does not have an integral which is bounded from minus infinity to infinity, so it's not in a square interval, and this is not a function.
Mm-hmm.
So no. Anyway. But there's still well-defined mathematics here. Integral from minus infinity to infinity of like Kronecker delta x minus lambda. Kronecker delta x minus mu, alright, dx is equal to b lambda on Earth squared Kronecker delta. What is this? What is this formula? What is that? What is that B? I don't know what that is, guys. I'm sorry. I've just got these notes. I don't know where that's coming from.
Yeah. How is it going to have a different magnitude than...
I would think it would just be... I mean, if I am allowed an analogy with the discrete case, with the finite case, if I've got Kronecker delta ij and then I've got Kronecker delta like, jk, and j and k are fixed, not summed over or something, then this is just because when can I and j be equal to 1 and j and k be equal to 1? It's only when I equals j equals k equals 1. So, if you think about it for a second, it's really just this, So I would kind of expect J is kind of playing the role here.
of x?
Yeah. So I was expecting it just to be like lambda minus mu over there, but whatever. This is beside the point, guys. I'm sorry. I'm sorry. I'm not talking about this. This is pointless, meaningless nonsense. I'm sorry. Let me go on. Sorry. Got sucked into my stupid notes. Okay, so the state, let me erase that before it causes more harm. Why did I even talk about all that green stuff? I'm very sorry about that.
I mean, the second part made sense, though, like with lambda in the...
Yeah.
That made sense, like if it matched up, but...
Right. I think... Okay, so here's the...
Sorry.
No, you're fine, it's fine. I think this is section 3.3. I really think this is probably from Griffiths, but I'll have to check. So point number 1, the state of a particle is represented by, and sorry, we really should have done this before I did the infinite square root with you guys, obviously, right? I'm sorry, if there's anything that unites this semester for you guys is that everything is out of order. Like we solved the problems before we developed the Fourier analysis. Now we solved the quantum mechanics problem before we developed the quantum mechanics. And I'm not sure what next. I'm sure it's going to be, this is like the Bizarro course. Let's see here. So the state of a particle is represented by this bra vector. This is a state in the Hilbert space. No, sort of. Possibly Hilbert space. I'll put some fine print on that one there. Anyway, so here's the idea. To each classical dynamic quantity, now, to a real devotee of quantum mechanics, they would say that this is irrelevant. Quantum mechanics is primary. So it doesn't have to justify itself. The fact that it produces classical mechanics in a certain limit is it. It's not that you start with classical mechanics and you produce quantum mechanics. This is just some kind of psychological bugaboo or whatever. I mean, it's just us being classical and unphysical from such a person's perspective. Anyway, classical dynamical quantity. You can associate an operator. Alright, so for example, for momentum, you represent that by h bar over I ddx. This is so-called p hat. Alright, kinetic energy. What does kinetic energy look like? It looks like p hat squared over 2m then. You remember that kinetic energy we can write as 1/2 mv squared, right? But do you guys remember that you can convert that to mv squared over 2m, aka p squared over 2m? Are you guys aware of that? I don't know if you're aware of that or not.
I can see it.
There it is. That's where that's coming from. It's just the 1/2 mv squared thing rewritten in terms of momentum, converted to an operator. That's the kinetic energy operator. But, of course, in terms of differentiation, that's minus h bar squared over 2m d squared x, dx squared. Alright, so the expectation value of an operator, alright, which I think we denote, well, he says just like that. I feel like, goodness gracious, I'm not sure if I'm supposed to put a hat there or not. I don't have a hat in my notes, I'll stick with it. I'm a little bit nervous about not having a hat there. Anyway, the expectation value of that physical variable we get from, this is basically an axiom, alright? We get from calculating psi star xt q hat psi star xt dx. That's what it looks like in the integral notation. In the bracket notation, this just looks like psi bracket q psi, q hat psi. So that's the probability that's the average value that of Q you'll measure. So if I was to calculate this for the position, right? For like the position operator, what would the position operator be? I'm not sure. Is the position operator Hermitian? Oh, sorry. There goes. Now, I mean, for this to be equal to its own conjugate, right? We have to have that. We have a Hermitian. In other words, Q hat has to again be a Hermitian operator, otherwise we get eigenvalues which are not real. Of course, psi doesn't have to be an eigenstate of Q either, right? If psi is an eigenstate of Q, then there's a definite value of Q that we measure. 2.2, which I will try to squeeze in here. 2. A determinate state. Not like determinant of a matrix, but like a determined state, okay? This is the definition though, has of Q, standard deviation of Q squared equal to 0. Now there starts to be some statistics in here. Maybe you'll recognize this. I don't know. I vaguely recognize it. It's been a while since I've done statistics, so here it is. It's Q. It's the expectation value of Q minus the average of Q, quantity squared. Does that look at all familiar? Have you guys done statistics or not? Like sigma x squared is something like the expectation of x minus the average of x squared, something like that. No? Maybe different notation. I don't know. Anyway, it's cool.
I have no idea what that is.
It's
But
like,
then again, I took the engineering stats.
oh,
I took 211, and it was, yeah, I don't know. I think it's probably different notation.
standard deviation, like the
No, yeah, that's
the
probably-
relation between like the standard deviation and the median, is it?
Yeah, it was in. Did it more in terms of like the bell curve stuff, but
Oh,
more
okay.
like graphically.
Well,
Which
this
is weird.
this right is going to be psi, and then we have Q minus bracket Q times Q minus bracket Q on psi. Can you see that? Is it too far over?
The camera actually is catching it.
Okay, cool.
Barely.
Then, but because Q is we're assuming Q is Hermitian, all right? So that's Q hat minus Q psi. I bring this one over here, and I leave that one there. Like that. And what we got then is, oh, stink, we shouldn't have to write that, oh well. That is exactly the length, right, of the vector Q hat minus the average of Q psi squared. So a determinate state forces this to be 0. What does that say about that vector? Remember? What do we get? We're about to prove something I claimed, in some sense.
You said that,
What's that?
you said that whole bottom line there has to be 0?
Yeah, well, it's 0 to start with by
Oh,
definition.
yeah, duh. Sorry.
And then, so this, if this is 0, if you have the length of a vector squared is 0, it forces the vector to be 0, right? So this gives us that Q hat minus Q psi is 0 itself, which is to say that Q hat on psi has to be equal to this on psi. Which says what? It says that a determinate state of Q hat is an eigenstate. And not just that, but this thing right here is the eigenvector, is the eigenvalue of it. Right? All right. Oh, goodness gracious.
So we kind of question about not knowing anything about this. Why is probability like such a thing that is like factored into here into quantum mechanics?
What's that?
Why is like probability like this like factored into quantum mechanics like this? Why?
Well, don't know, it's basic to quantum mechanics. I don't know how to answer that.
Is that called?
I mean, quantum mechanics is the very nature of quantum mechanics is statistical. And so you can ask, why is physics statistical? I don't know.
Maybe I don't understand that question.
Maybe I don't understand the question. It's possible. In fact, it's probable. Let's see here. Oh, hey, that was unintentional.
No way.
Actually, it was. Now, there's different kinds of examples in quantum mechanics, like the state space. It can be some kind of like continuous spectra of states, right? But there are other examples where there are like a discrete spectrum of states, like that simple, the infinite square thing we did. We didn't have a continuous spectrum of eigenstates. We had like the n equals 1, 1, the n equals 2, n equals 3, n equals 4 as a discrete spectrum of states. So, sort of typically, if you're working with a system which has got sort of like boundaries, you'll tend to get a discrete spectrum. If you don't have boundaries, if you don't have edges, then you'll get a continuous spectrum.
So where you said that like it showed that like energy was quantized in that respect. Is that discrete?
Yeah.
Kind of thing? Okay.
Yeah, and alongside that, exactly. I mean, the spectrum is the eigenvalues. The eigenvalues are those things that we think of classically, things that we measure. They're the measured value of the quantum mechanical operators. I mean, they're okay. So I think we can come back to Schrodinger's equation now a little bit. There might be enough time here to derive at least one thing for us. Sorry if it seems slow. We're about 3 weeks into quantum mechanics. Well, I guess it depends on where you're taking it, but so Schrodinger's equation, right, says IH bar partial psi partial t is equal to minus h bar squared over 2m partial squared psi partial x squared plus the potential energy for the system m psi. This is Schrodinger's equation. Here, h bar is h over 2 pi, and that's approximately 1.05 times 10 to the minus 34 joule seconds. So that's a lot of the reason we don't have to talk about this in physics, because it's super small. And it's not something you run into macroscopically that much, right? Now, so what does psi mean? Basically, here's the interpretation. Psi of x comma t squared dx. What does this mean? This is equal to, here it is. This may be helpful to you, Jess. Is the probability, it's the probability of finding the particle between x and x plus dx at time t. That's what that means. The particle must be found somewhere, so we have that the integral from minus infinity to infinity of the of psi star psi is equal to 1, right? Now, if this notion, right? So there's an immediate question, like, this is allegedly the equation that governs the evolution of the wave equation through time, right? We're supposing that the probability of the particle somewhere is 1. The question is, are these two things consistent? How can we check that Schrodinger's equation is consistent with this probability interpretation of the wave function? The better answer to your question